fin can produce force due to the upstroke and downstroke in both times. This figure is the force, the total forces in different frequencies and fin angles. One thing is mentioned over here, you can see at a frequency at the 30-degree angle, this line is very near to zero. This is also consistent with our experiment, that is because our experimental self-propulsion frequency is also very near to this value. Here I showed the total force in different aspect ratios and different fin angle. Here you can see these two lines give the similar value, that is at 0.075, 45 degrees, give the same value as aspect ratio 0.1 and 30 degrees. From this video, I tried to show the pressure difference distribution of the fin when in different conditions. You can see here. When we increase the frequency and or the fin angle, it makes more pressure difference. That is shown by deeper color. This, to understand the pressure difference very clearly, we cut the fin in the z direction, y direction, where y is equal to 0.275. So that is the P4 position. We cut it. And here you can easily see the negative and positive pressure difference by green and red color. The pressure difference is very important for fast calculation. I will discuss it in the next slide. Before that, let's see the corresponding velocity distribution here, relative boundary layer shape here. As I mentioned in the previous slide, the pressure difference is very important for fast calculation. Here you can see the thrust calculation. The thrust is calculated by the pressure difference. This is calculated by upper minus lower surface ratio, multiplication by the normal vectors or x direction, that gives the pressure difference. These two figures shows the pressure. This figure is the pressure difference control, and this figure shows the thrust force distribution control. From here you can see one red color and green color, one red color and green color. That means one times negative pressure difference, positive pressure difference. But this figure, both are red color. That is the highest pressure. This is also consistent in my previous slide discussion, that is during the upstroke and downstroke, that is negative pressure difference, positive pressure difference, both times it gets the maximum thrust. From this figure I want to also note that where the body has the pressure difference, the body doesn't make the thrust because of the normal breaker here. Now let me point out about the fin open characteristics. We also find this KX, that is thrust coefficient versus advance coefficient, similar to Poplar chart. This is the figure in the aspect ratio and maximum fin angle 30 degrees. Here one thing is mentioned about this KX is the force produced by fin in x direction. And average value, there is converse period in average value x. So here the result is change of result is expected. And this figure is the same result, but just change the angle to 45 degrees. Now let me discuss about the relationship between KX and aspect ratio. This is a derived formula. From here you can see the thrust coefficient is proportional to the cube of the aspect ratio and square of the fin angle. Let me discuss. If we divide 0.1 by 0.075, its cube is 2.37. That is, if we divide the result of 0.1 using this value, it will go very near to this value. Say that the 500 K also. Now relation between Kx and maximum fin angle. Kx is proportional to the square of the maximum fin angles. That is, if we divide 45 degree minus 30 degree, but the square is equal to 2.25. That is, if we can divide the 45 degree result using 2.25, the result very close to the 30 degree result. Comparison with our experimental result. Here, In this computation, we calculate the experimental result, computed result, and calculated result. The experimental results of model 3 and model 4 with the corresponding aspect ratio 0.166 and 0.09 are shown by dot line. And our computed result of aspect ratio 0.075 and 0.01 are shown by violet and red line. As there is the difference between our computed aspect ratio and the experimental aspect ratio, we try to make it similar as by calculating using the previous formula. So this is same as model 4 calculated result, this is same as model 3, that is shown by the dotted line. In the first side, you can see some differences between the legends, but this is very obvious because there are many differences between the computation and the experimental result. From the video or picture from the robot, you can see the body is stick body, and in the stick there are many sticks that makes resistance. But you consider here only the flat plate with no resistance. This is the same result, but for the 45 degree. Here you can see there are little it improved. The comparison is improved. This is the clarification is. If we increase the angle, the same area can produce more pressure. For this reason, here the result is more accurate than the degree result. Finally, conclusion. We have 3 objectives. So the corresponding conclusions are a computational code was developed that can compute the flow physics around undulating side fins. A simple relationship among the undulating side fins is particular and hydrodynamic force was established. And the thrust force distribution on the surface of the fin was analyzed. These results will be implemented to improve the design of the model. And in future, we already make fin. Here we use the flat plate. We already made the fin like the model, very similar to the model, and we try to improve our code to overcome the limitations I mentioned. Thank you very much for your kind attention.
Thank you very much for that, your report of your work on the means of propulsion that has been around for quite some time, and I look forward to seeing it in a proper ship as opposed to a model. We have time for one question, 12 plus 2. Are there any questions of the speaker?
I'd like to know if the model is
The question, in case you hadn't heard, was the model 2-dimensional or 3-dimensional?
Model is considered 3-dimensional. Yeah. Because the thing it has Z direction.
One more question?
Is it a self-starting force, or do you have to have forward speed? In your modeling, did you use forward speed as constant?
Yes, I already mentioned in one.
I understand.
Yeah. Actually, in our computation, we make a fit to the body and the force. It includes actually suggested force because there is 1. But first we increase from 0 to 1, then make it suggested velocity. It is suggested 1. Yeah. Thank you very much, sir.
Thank you very much indeed, and please join me in thanking again the speaker for a very interesting presentation. And our next speaker could come forward.